In this video, we'll take a look at why horizontal transformations are always kind of the opposite or the reverse of what they seem like they should be. There's this kind of counterintuitive nature to horizontal transformations where the result is always kind of backwards from what it looks like it should be. And we'll do that by taking a look at a horizontal shift. Of course, the same reasoning applies to horizontal stretches and compressions or whatever. And we'll use the function y equals the square root of x. And you could use any function you want. I'm just choosing y equals the square root of x for this example. So we have a graph of y equals the square root of x right here on the screen, and we're going to take a look at transforming that. And why don't we transform it we'll do a shift 4 units to the right. So we'll have the y equals the square root of x minus 4, which I'm sure you recognize as being a transformation of y equals the square root of x 4 units to the right. But the question we want to address here is why does doing x minus 4 here end up shifting the graph to the right and not the left? I mean, the minus or the negative, however you want to think of it, kind of implies a leftward motion, doesn't it? I mean, left, when we take away something, we usually go left on the number line. So why doesn't changing our function to the square root of x minus 4 move the graph to the left? And we know it doesn't. It actually moves it to the right. So to figure this out, let's take a look at some specific points on our graph of y equals the square root of x, specifically ones that are easy to work with. For example, 0, 0, 1, 1, 4, 2. Of course, I'm picking x values that are nice for taking square roots, 9, 3, and 16, 4. All right, let's take a look at each of these points. Well, not necessarily all of them, some of them. And we'll start with this one right here, 0, 0. And I want you to think about what is that point's y value. Well, that's easy to answer. It has a y value of 0. And how did we get that y value of 0? We used an x value of 0. That is, when x was 0, well, the square root of x is the square root of 0, so we got a y value of 0. What would happen in this function if we wanted to end up with a y value of 0? What x value would we use to get a y value of 0, just like we did in the base function? Well, it's not going to be an x value of 0 like it was here, because if you do 0 minus 4, you're going to get negative 4, and the square root of negative 4, well, that's not even a real number. So it's not 0. What we want to end up with is a 0 under the square root. Now, how would we do that? Well, it's pretty easy to see. We'd have to use an x value of 4, because 4 minus 4 is 0, and then that's the square root of 0, which would give us a y value of 0. So we had to use an x value of 4 here to get that y value of 0. All right, so think about that for a second. Over here in the base function, an x value of 0 got us a y value of 0. But in the transformed function, if we want to get a y value of 0, we have to use an x value of 4, which is 4 higher than this x value. And why did we have to use an x value that was 4 higher than this to get that y value of 0? Well, kind of to accommodate or account for the fact that we're subtracting 4. We need to use an x value that's 4 higher to kind of undo that effect of subtracting 4. And if we graph that, well, what does that end up looking like? Well, it means we need to use an x value of 4 to get a y value of 0. And doesn't it look like that point that was originally 0, 0 moved 4 units to the right? Yeah, we had to use an x value that was 4 higher. Okay, well, that was good. Let's try it with another point now. I will just erase some of that work there and clear things up a little bit here. Okay, let's use the next point on our graph. Let's use 1, 1. Okay, so again, take a look at that point 1, 1 and think about what its y value is. Well, its y value is 1. And how did we get a y value of 1? We used an x value of 1. That's pretty straightforward. The square root of 1 is 1. Now, looking at this function, say I'm interested again in the point that has a y value of 1. What x value do I need to use to get it? Well, it's not going to be 1 like it was here because I'm subtracting 4. So if I want to end up with a 1 under the root, like I did here, I need to use an x value of 5. Right? 5 minus 4 would give me 1, and the square root of 1 is 1. Again, notice the x values they differ by 4. This one here is 4 higher than this one here. Why was that necessary? Well, kind of to undo the effect of subtracting this 4, to account for the fact that I have x minus 4 under the root. If I want to get that old y value, I got to make an x value, or I got to use an x value that's 4 higher than it used to be in the other function. So take a look again. If we use an x value of 5, we get a y value of 1 here. So that means the point on the transformed graph will be 5, 1. And again, doesn't it look like that point moved 4 units to the right? Absolutely. Okay, and we can keep doing this. Maybe we'll just take a look at one more here. This point here, 4, 2, that has a y value of 2. It came from an x value of 4. If I want to get a y value of 2 now, well, because I'm subtracting 4 here, I have to use an x value that's 4 higher than it used to be, 4 higher than that, which is going to be 8. All right, and that means, and you can check it, 8, if you do like 8 minus 4 right here, that gives you 4, and the square root of 4 is 2. So it does actually work out to a y value of 2. So the point 8, 2 will be on my transformed graph, and again, it makes it look like this point shifted to the right 4 units. And that'll always happen. That'll happen for all of them. That's why we end up getting a graph that looks like it's been shifted, and that's pretty inaccurate, but shifted to the right 4 units because we had to use x values that were 4 higher than what they used to be here to get those old y values. And this also applies to horizontal stretches and compressions. Just for example, if we had y equals the square root of, let's say, 2x, that is a horizontal compression of factor 1/2. Why? Well, because in order to get the old y values that I used to get with this function, I now have to use x values that are half of what they used to be to account for the fact that I've got a times 2 or a multiplication by 2 in there. And when I use x values that are half of what they used to be, I get the look of a horizontal compression, not a stretch of factor 2, but a halving, a horizontal compression of factor 1/2. So there it is. There's kind of a little bit of an explanation as to why horizontal transformations are the opposite, or they end up looking like the opposite of perhaps what they should be. I hope you found that helpful. I hope it wasn't too confusing. There you go. Take care.